All right, here we go. So today we're going to learn about work done by conservative forces. So just to really quickly sort of put this in context, in the last video, what we learned was what's called the work kinetic energy theorem. It said that if you calculate the work done by the net force, i.e. the total amount of work done on an object, then the net work would be equal to your change in kinetic energy. Okay. So an interesting way of thinking about your network, remember your network is the total of all of the different works done, the work done by force number one, plus the work done by force number two, etc. So we can also break that up. We can say, well, the network is the work done by all of our conservative forces, plus the work done by all of our non-conservative forces, okay? And so in the last video, we focused on this element. In this video, we're going to focus on the work done by the conservative forces. All right. So to do that, we need to first learn what is a conservative force. All right. So what's the difference between a conservative and a non-conservative force? So the kind of short answer, and the answer that I give my honors students is this. A force is conservative if it has a form of potential energy associated with it. Okay. So the force of gravity is a conservative force because gravitational potential energy is a thing. Okay. The force of elasticity, spring force, Hooke's law. Oops. The force of a spring, an elastic force, is conservative because elastic potential energy is a thing. Okay. So that's kind of a half answer. But then the question is, so if we can do that, then why don't we just make frictional potential energy a thing and then call friction a conservative force? And it turns out that you can't do that, okay? Which is what this says up here, okay? Why don't we just make frictional potential energy a thing and make friction a conservative force? And you can't do that. So the reason is this. The textbook definition of a conservative force is this. A force is only conservative if the work done by that force as you move an object between 2 points doesn't depend on the path followed, okay? So if I move an object from point A to point B, no matter how I get there, if I go straight from A to B, or if I follow some curvy path, or if I go out and up and over, no matter what, if I travel from point A to point B, the work done by a conservative force will always be the same, but a non-conservative force will not, okay? So let me see if I can run through these numbers relatively quickly. I don't want to get too bogged down with this because it's really not that big a deal. But so long story short, so in this first example here, we've got Roy. He's going to lift a 4-kilogram box up 5 meters. Okay. So here's my 4-kilogram box. Force of gravity on it is going to be negative 39.2 newtons, just 4 times 9.8. And we're going to move it up through a vertical displacement of 5 meters. So I can calculate the work done by gravity. Work done by gravity is the force of gravity times the vertical displacement. Notice I'm focused here on vertical displacement because gravity is a vertical force. So I'm going to get negative 39.2 newtons times 5 meters gives us 196 joules, negative because the force is working against the displacement. Cool. All right. Now, in the second example, what we're going to do is we're going to still lift it up 5 meters, but we're going to take a different path. So here's what we're going to do this time. This time we're going to go up 7 meters. And then we're going to go to the right 3 meters. Down 2 meters. And then back to the left another 3 meters. Okay. And so what ends up happening here is if you find the work done during this red chunk going up 7 meters, that's going to be negative 39.2 newtons. That's the force of gravity times 7 meters up. So that's the red part. I'm going to jump ahead. Let's do the black part. During the black part, our force of gravity is still negative 39.2 newtons, but now my displacement is down 2 meters. Oh, I kept right up writing my answers, didn't I? All right, so if you do this one, it turns out to be 78.4. The red one turns out to be 274.4. Right? And then it turns out that during both the blue and the green, the work is 0. Because for both the blue and the green, the displacement is horizontal, but the force of gravity is vertical. So they're perpendicular to one another, right? Remember, anytime your displacement is perpendicular to your force, the work done is 0. All right. And so if you add all of these up, negative 274 plus 78 plus 0 plus 0, you get negative 196 joules. And so the point is, in both instances, we lifted our box up 5 meters, we followed different paths, but the work done by gravity was still the same. And as a result, gravity is a conservative force. Okay. Now, I'm not going to run through an example, but it turns out springs kind of have the same property. If I take the spring and stretch it a big amount and then back a little bit, the amount of work done by the spring is the exact same as if I had just gone directly from here to here. Okay. I'm not going to run through the work or the calculations on it simply because the force of the spring is not constant. So the calculations are a little bit more complicated, but it does work out with kind of similar rationale. All right. So I guess the next thing I want to do then is, so then why is friction not a conservative force? Why is friction not conservative? All right. So suppose I've got a block sitting on a table. So I'm going to do top view. All right, and here's my block. Let's suppose that the force of friction on this block is, I don't know, let's go 10 newtons just for simplicity. All right, and I'm going to try to move it from point A over here to point B, which is a displacement of, I don't know, let's go 4 meters out. Okay. So if I go straight there, then what's going to happen is, as the block slides, my force of friction is going to be backwards 10 newtons. And so the work done by friction, if I follow that black path there, is going to be my force of friction, negative 10 newtons to the left, times a displacement of 4 meters to the right, gives me negative 40 joules, right? Okay. Now, suppose instead, I go from point A to point B by going 4 meters this way. Then I go 4 meters this way. You know what? Let's do that one in black again. Well, I guess it doesn't matter. 4 meters this way. And then 4 meters this way. Well, the idea is in this, so this is going to be the same end result, right? We're still going to end up 4 meters to the right of our starting point. But the difference is that in each of these 3 legs, the work done by friction is going to be negative 40 joules, right? Because if I'm going down, then my friction's up. So for this red chunk, the work of friction is going to be negative 40 joules. Then for the green chunk, we're moving right, friction is going to be to the left. The work of friction for the green chunk is going to be negative 40 joules. And then for the purple chunk, when I'm going up, friction is going to be down. So now my work of friction is again negative 40 joules for a total of 40 plus 40 plus 40. Now the work done by friction is negative 120 joules, right? Because our distance increased, friction had sort of a larger distance over which to do work. And so even though points A and B were the same, the work of friction does depend on the path here, okay? So friction is not a conservative force. Cool. All right. Cool. Now, it turns out that when work is done by a conservative force, like gravity or a spring, the work done by that force changes the potential energy associated with that conservative force. In other words, when gravity does work, your gravitational potential energy changes. When a spring does work, your elastic potential energy changes, okay? And it turns out it gives you this relationship. The work done by your conservative force is the opposite of the change in your potential energy, okay? So by opposite, it means opposite sign. So if gravity does negative work, you gain gravitational potential energy. If a spring does positive work, you lose elastic potential energy. Okay, so the sign of the work is the opposite of the sign of the change in potential energy. All right, so let's do a quick example here. In fact, let's revisit one that we just did. Let's do the 4 kilogram box being lifted a distance of 5 meters. So this is the example we just did a minute ago. 4 kilogram box being lifted a distance of 5 meters. So the work done by gravity is the force of gravity times the vertical displacement. That was negative 39.2 newtons times 5 meters, gives you negative 196 joules. What's the change in gravitational potential energy? i.e., what's the change in gravitational potential energy? Just refreshing your memory about the 2 different types of notation that you'll see, sort of collegiate level and honors physics level, right? So change in GPE is mg delta H. So let's see, the mass is 4 kilograms. G is 9.8 meters per second squared. Our change in height is positive 5 meters. And you get positive 196 joules. There you go. So notice our change in gravitational potential energy is equal but opposite the work done by gravity, because one is negative 196 and the other one is positive 196. All right. All right, so sorry, parched. All right. So let's do an example with a spring here. Okay. We are going to need some more room. So okay, so all right, sorry. Custodian came in. I hope that didn't record. I wish I could edit. I can't. Thank you, Grosse Pointe Public Schools. Okay. All right. So here we've got a 5 kilogram mass on a 30-degree inclined plane, and it's attached to a spring with a spring constant of 80 newtons per meter. All right. The mass has been lowered until the spring supports all of the mass's weight. All right. So I probably should have given a drawing on this one. I'll go ahead and make a drawing for you. If this had been a worksheet, I would have had to have done that. So, but here's what I was envisioning when I wrote this. We've got a block on an inclined plane attached to a spring, and that spring is attached to a wall, right? And so right now it is positioned such that the spring is supporting the weight of this thing, okay? Let's see, what else do we know? It doesn't explicitly state it. Let's assume that the inclined plane is frictionless. Right? So this is a 5 kilogram block. So we're going to split it up into components, right? So there's an FG perpendicular that I don't really care about because it's going to cancel out the normal force. We've got our FG parallel, which if you calculate it, turns out to be 24.5 newtons down the hill, which means that the force of the spring must also be 24.5 newtons, right? Because it's supporting the weight. And so now what I can do is I can go, oh, well, I know the force of the spring is negative K times X. So the force of the spring is 24.5 newtons. Our K value is 80 newtons per meter. Oops, newtons per meter times X. Divide both sides by negative 80. And what you discover is that the spring right now is stretched by a distance of negative 0.306 meters. Again, that negative sign, the negative sign is just telling me that the spring is stretching down, right? All right, and then I guess finally, because seriously? All right, wow, that was a lot of work. All right, so what's happening then is the object is going to go, so as the spring stretches, we're going to go this way 0.306 meters, which means we have a vertical displacement, right? Because this is 30 degrees. So we're going to move down 0.306 times the sine of 30. So you get 0.153 meters. So that's our change in y, which is the same as our change in height, right? Okay, this is going to be important because it's going to determine our change in gravitational potential energy. Okay. So let's go through and do a couple quick calculations. All right. Sorry, here we go. So part A. How much work does the spring do as the weight is lowered? So I'm going to calculate this the way that, like, without making any assumptions. All right, I'm basically verifying this result. Okay, so I'm going to calculate the work done by the spring using what we know. So here we go, part A. So the work done by the spring, all right, remember the force of the spring is not constant. So that's equal to the integral of the force of the spring with respect to the position, which is equal to the integral of, let's see, negative 80x dx, and the spring gets stretched from a relaxed state to a distance of 0.306 meters. If you want to be really particular, I guess technically it is negative, okay? All right, so when I integrate this, let's see, the integral of negative 80x is negative 40x squared. And I'm going to evaluate it at 0 and negative 0.306. Notice the negative here is going to get squared, so that doesn't actually really matter. So plug in your numbers and analyze this, and you get negative 3.75 joules. Okay, so that's the work done by the spring. All right, part B, by how much does the elastic potential energy change? Well, the starting elastic potential energy is 0 because the spring wasn't relaxed or wasn't stretched. But then as the weight stretches it, we gain elastic potential energy. So our change in EPE is 1/2 kx squared. That's 1/2 times E times negative 0.306 squared, and it gives you positive 3.75 joules. And so once again, what we've discovered here is the work done by the spring is equal to the opposite of the change in elastic potential energy. Okay. All right. And then how much work does gravity do? So let's do C and D. So C, how much work does gravity? Well, the work done by gravity is Ft parallel times the displacement. So negative 24.5 meters down the hill times negative 0.306 meters down the hill gives you 7.5 joules. And then part D, what's the change in GPE? Well, that's mg delta H, which is the mass of the block, 5 kilograms, times G, 9.8 meters per second squared, times our change in height, which you will recall was this negative 0.153 meters. Multiply it, and you get negative 7.5 joules, which is what we would hope we would get. All right, so yay, physics. All right. So this elastic potential energy equation that we came up with here kind of gives us, it's not even really a new calculus equation, but I guess it's just worth commenting that sorry, I wrote it on my paper. Okay, so here's what we know. We know that if you integrate a force with respect to position, it gives you the work, right? And so for us, if you integrate a conservative force, it gives you the work done by that conservative force. And that is what we've now learned, equal to the opposite of the change in potential energy associated with that conservative force. All right, so there's nothing really new there. I guess I want to emphasize that we still have this property that if you integrate a force, it gives you the work done by that force. The additional thing we now know is that the work done by a conservative force is the opposite of the change in potential energy. Okay, so suppose a conservative force is given by Fc equals 4x cubed minus 8, where F is in newtons and x is in meters. You can find the change in potential energy between these two positions. Okay, so I'm just going to follow this idea. I'm going to go, all right, well, the work done by my conservative force is the integral of the conservative force with respect to position. So that's the integral of 4x cubed minus 8 with respect to position between 1 and 5. So take your integral and you get holy moly, we still have a ways to go. So you get x to the fourth minus 8x evaluated at 5 and get 1. So plug in your numbers and you end up getting 593 joules. Cool. So that's the work done by the conservative force, which means that the change in potential energy associated with that conservative force is negative 593 joules. All right. And my recommendation is to do what I did here. Do it in 2 steps. Find the work and then change the sign to get the change in potential energy. All right. So that's a pretty common type of problem. Right? Let's go the other way. Suppose I give you the potential energy equation. So this one takes a little bit of mathing, I guess. So I know that force is the derivative of work with respect to position, which means my conservative force is the derivative of the conservative work. Oh, that's equal to the derivative of the potential energy, opposite sign though, right? With respect to position. Okay. So, what that means then is the derivative of my potential energy with respect to position is the opposite of the conservative force. So if I take the derivative of this, let's see, dUc dx is the derivative with respect to x of 2x cubed minus 8x. What is that? 6x squared minus 8. So that's the opposite of my conservative force, which means the conservative force is negative 6x squared plus 8. And so now I can just plug in my position. What were we trying to find here? So at x equals 2, just plug in your numbers. So you can get negative 6 times 2 squared plus 8. So negative 24 and 8 is what negative 16 means. Okay. So those negative signs are a little bit tricky. Okay. Again, I always go through work and then just remember that the work is the opposite of the change in potential energy. Okay. It's a little bit weird here because here you've got the change in the change, whatever, it doesn't matter. Okay. We are almost done here. Holy moly. Sometimes you'll get this all graphically. All right, let's go back to one screen here. All right, so the graph here shows a conservative force as a function of position. So this is my conservative force. This is the position. The object's potential energy at x equals 4 is 20 joules. So we know that the potential energy associated with our conservative force at x equals 4 is 20 joules. And we're trying to find the potential energy at x equals 0. Okay. And so what I want to remember here is, let's not worry about part B. Part B is basically the same idea. So what I want to remember here is that if I integrate my conservative force with respect to position, that gives me the work done by the conservative force. That's the same as the opposite of the change in potential energy. Oh, and this integral just means area. So let's find the area between x equals 0 and x equals 4. Here's my little triangle. So this area is going to be half of base times height. So my base is 4, my height is 8. So 2 times 8 has an area of 16. So what we've just learned here is that the work done by my conservative force is 16 joules, which means that my change in potential energy is negative 16 joules, right? And I know that my change in potential energy is final minus initial. So final minus initial. So U of 4 minus U of 0. So let's plug in our numbers. So we get negative 16 equals 20 minus the potential energy at 0. So I don't know, add and subtract, and we get the potential energy at x equals 0 must have been what, 36 joules. Okay. And then part B is similar, except you're gaining energy instead of losing it. All right. And then finally, last example, the graph here shows the potential energy of a thing. Sorry, it's getting late, getting lazy with my examples. So it says find the force associated with the conservative force. So here's what we know. We know that a conservative force is the derivative of the work with respect to position. That's the opposite of the derivative of the potential energy, or the potential energy with respect to position. So it's the opposite of the slope. So at x equals 3.2, we're here. So let's go ahead and find our slope. Our slope is rise over run. So let's see, our rise, we're going from 12 down to 4. So that's negative 8 over 4. So negative 2. So negative 2 joules per meter. Remember, a joule is a Newton meter. The negatives cancel, so you just get 2 newtons. Okay. All righty, that's what I got for you.